Corrosion is yes. The oxidation of a metal, yes. So, in order for corrosion to occur, you need what two things? You need oxygen. You need a metal. And finally, you need water, because if everything's just dry, 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 it won't happen at all. A salt will help speed up the process of corrosion, but it is not absolutely necessary. Honestly, we could go into writing the reactions. I don't think you're going to absorb any of it, so I'm going to skip that part. If you're interested in seeing the reactions, you are going to watch the video that is attached to 6.5a. Okay, 6.5a will show you all the reactions, and it will give you the actual process. We might watch it after we're done this. But what you do need to know is that what is the oxidation of iron? Please tell me what the reaction is for the oxidation of iron. Okay, you can have either of those. Yes? All right. So that's basically what's happening there. And do you guys know what happens when things rust? What does it look like? They got all brown and crusty and gross, yes? So we would like to prevent corrosion. What is one way you could prevent corrosion? How do you prevent your car, which is made of steel, not stainless steel, but steel, how do you prevent your car from rusting? You paint it. Yes, you just provide a physical barrier, okay? How does that work? It stops your oxidizing agent from getting in contact with the reducing agent. So there is a physical means of preventing corrosion. There is also a chemical means. And it is called cathodic protection. And by means, I don't mean it means something. I mean, it's a way of doing it, chemical way of doing it. Yes?
So when we lift that off, would that be electroplating or sacrificial?
Either. Okay? So you can either, if you electroplate it with another metal, that does both physical and chemical. We'll get to that in just a second. Okay, so we have a physical barrier, we have a chemical means, and then if we have our iron here, Fe, let's say we attach to it a block of Zn. It doesn't really matter which metal it is, as long as this metal must be more easily oxidized than iron. So in other words, it must be a what reducing agent? It must be a stronger reducing agent. Yes. So let's go look at our chart. So if we're trying to protect iron, here is iron here. Anything that is lower than iron, so let's say we have chromium, we have zinc, manganese, aluminum, magnesium, sodium. I can't imagine you coating something with sodium. It would explode if it came into contact with water. Yes? So pick something that would be reasonable. Let's just leave out these ones at the bottom because they're all somewhat reactive with water. Okay? And when I say reactive, I don't just mean a little bit reactive. I mean like could explode possibly on you. Very reactive with water. Not a good choice for we call it a sacrificial anode. So who would be good choices for a sacrificial anode? Chromium, zinc, manganese, aluminum, and magnesium. And why do we call it a sacrificial anode? Have a chat amongst yourselves. Why do we call it a sacrificial anode?
It's like the air of the cell.
What?
So the anode doesn't have to be in a cell. There's like no cell here. And it's the air.
No, but there would be maybe some water or something, right? There's going to be like, moisture, right? Drips of water. the sacrificial anode gets oxidized instead of iron because it has a higher oxidation potential. Yes? And so it disintegrates. Yes? So it would be over time. Zn solid goes to Zn 2 plus 2 electrons. Yes? And so what has it done? It has sacrificed itself. Yes? It has been sacrificed. Now, what happens when all the zinc is gone? The iron is going to then start to corrode. Okay? And so the reason we would have to replace the zinc. So if you have a sacrificial anode, say on your boat propeller, this is a good way, because a boat, you know, it's the propeller is going to get banged around by a lot of things. So painting the boat propeller might be useful for a little bit, but it's not going to completely keep this boat propeller safe from corrosion. So if you attach to it a block of magnesium or a block of zinc or a block of chromium, now you have something else that will oxidize instead. And so every time you would take your motor out or your propeller out of the water, you would need to check the area where the sacrificial anode is attached and make sure there is still enough of it left to do its job. Yes? Yeah. Yeah. So the sacrificial anode can be any one of the zinc or the magnesium or anything that's lower on the chart. Oh, the whole propeller? Expensive, number one, and not as sturdy, number two, right? So, yeah. Oh, and the other thing is, too, that now you have the problem of zinc, like, becoming oxidized. Although zinc oxide actually zinc oxide, rather than being all crusty like iron, it forms a protective layer on the top. So once you have zinc oxide on the top, you won't make more zinc oxide because now the oxygen can't get to the zinc that's below the zinc oxide. The reason iron oxide is such a problem is you end up with flakes, right? And then it peels off and reveals the metal below, and you end up with air bubbles in between the flakes where the water can get in. So that's why iron oxidation is such a big problem, right? It just keeps kind of going and going because it destroys the structure of the top layer. Whereas zinc or something else, just the top layer just oxidizes and then you have that oxide and it's flat and nice and stable. Yes?
So then if you use zinc as, I guess like a sacrificial method or whatever.
Yeah.
Once it becomes zinc oxide, would you ever need to replace it?
You will eventually, like, what's going to happen is that in the water, say, the zinc is going to come off as Zn2+. It's not going to stay there as zinc oxide, and so it'll just, like, drift out into the water, right? Now, there is a process by which we combine both the physical and chemical means. And so it is either electroplating or painting your iron with zinc. Yes, or aluminum, or something like that. So now you've provided a protective layer, right? But if it gets scratched, like if you scratch paint, you just have bare iron, yes? But if you scratch the zinc, now you have zinc on either side of the scratch. The zinc oxide will form and it will fill in that scratch. And so it's actually sort of like a self-healing kind of a deal there, okay? So it's kind of nice because, yeah. Now, did you want to watch Colger's videos on this process? Yes? Okay. If you have already watched this at home, feel free to carry on with whatever review you're doing.
Corrosion is the unwanted oxidation of a metal. Oxidation of all metals in general is called corrosion, whereas oxidation of iron metals specifically is usually called rusting.
Okay, so this is, if you want to follow along in your book, this is on page 130, 130.
Looking at the standard reduction table, near the bottom, we see that iron, zinc, and aluminum are all near the bottom right. They all have high oxidation potentials, which means they are strong reducing agents, and are readily oxidized. But notice that aluminum and zinc don't seem to corrode like the iron in steel does. It's because aluminum and zinc both readily oxidize to form hard oxide coatings that are difficult for more oxygen to penetrate.
Okay, so that's what we were talking about with the zinc oxide forming a lovely coat on the outside that the oxygen just can't get through.
So these metals will not corrode much under normal atmospheric conditions, even when they get rained on. But iron, or Fe solid, is different than other metals like aluminum and zinc. Its oxide does not form an impenetrable coating. Instead, it can flake off, exposing a fresh iron surface to oxidizing agents. Steel is mainly iron. Coating steel with tin protects its surface and prevents oxidation of the iron that's in it. This is why tin cans, which are tin-coated steel, are normally good for keeping food without rusting.
Is anyone writing stuff down and wants me to pause?
Go back to
Yep. Yep.
Fresh iron surface to oxidizing agent.
Is good? Cool.
Steel is mainly iron. Coating steel with tin protects its surface and prevents oxidation of the iron that's in it. This is why tin cans, which are tin-coated steel, are normally good for keeping food without rusting. However, if the cans are dented or pitted, the tin coating is broken and water can collect in the indentations. Now rusting occurs relatively quickly. We'll consider a piece of iron where a dent or a crack in a painted surface makes it easy for a water droplet to come in contact with the iron surface. Here, an iron atom can oxidize to an iron 2+ cation, which will dissolve in the water. The equation for this oxidation is Fe gives Fe2+ plus 2 electrons.
We good?
Further oxidation of iron here causes pits in the surface to increase in size. What is formed here is an electrochemical cell. Because oxidation takes place here, this is called the anode region. Oxygen from the air can come into contact with the edge of the water droplet and the iron metal surface. If we could take this section of our standard reduction table and split it right here, we could add in this half reaction. It is the reduction of oxygen in the presence of water to produce hydroxide ions.
Okay? Where'd we go? There we are.
And its reduction potential is positive 0.4 volts. Here, oxygen combines with water and the electrons formed by the oxidizing iron to form hydroxide ions, which then dissolve in the water droplet.
So you can see what are the three things that we need for corrosion to happen. We need iron, or a metal. We need oxygen, and we need water.
Because reduction is taking place near the point where the water, iron, and air meet, this is called the cathode region. Looking at the solubility table, we see that Fe2+ and OH- form a low solubility compound. The Fe2+ ion formed at the anode can combine with the hydroxide ions formed at the cathode to produce the precipitate FeOH2, which can build up on the iron surface. What can happen is oxygen from the air and water in the droplet can act to further oxidize the iron in iron 2 hydroxide, and through a fairly complex series of reactions, form what is called hydrated iron 3 oxide.
So are you going to need to know those complicated reactions? No. In fact, you are not going to have to know the oxygen plus water gives hydroxide, because if they want you to know it in AP, they will give it to you. Yes, you're not going to have to pull that out of your ear or whatever, okay?
Which has a formula Fe2O3.XH2O. The X
We are on page 134.
Wait, no, on that blank.
What?
I knew you're on.
Oh.
Before, but I was like, some of these blanks sound like.
I don't actually know. All I know is you got to fill in anode region, cathode region. We've got a blank for the oxidation of, or for the reduction of oxygen and water together. Reduction takes place at the point where the water, iron, and air meet. So this area is called the cathode region. Oxidation occurs at the pit. So the pit is called the anode region.
It's like that blank, the same space as the anode region, like also anode region. It's like the same blank.
Which, what, where, who, ha?
It's kind of like.
Which number are you on? Like it says 1, 2, 3, 4, like the diagrams are labeled?
I'm looking at like 1 and 2.
1 and 2, gotcha. Okay, I don't know why there's an anode region labeled up above. The little Fe turns into Fe2+ in diagram 1. And over on the right, we're going to put O2 in that little circle in number 2.
And then ignore the first anode region blank.
No, whatever. Doesn't matter.
And then for 2 continued.
Yes. You're just filling in the reaction of the 1/2 O2 plus 2 H2O.
Is that the same reaction in both blanks?
Yep.
Okay.
Always.
And that's basically it for this one. Shall we talk corrosion prevention?
Really?
136.
In this video, we're going to look at corrosion, and in particular at why things rust, and how we can prevent it. Corrosion is a general
What is corrosion? Where are we now? Conditions for rusting. How to stop iron rusting. That's where we want to be.
The last thing we need to look at is how we can prevent iron from rusting. Generally speaking, we can split the methods into two main categories: barrier methods and sacrificial methods. The barrier methods work by preventing the oxygen and water from ever touching the iron, so that rusting can't take place. And there are three main types to know. One is to paint it, which works well for really big pieces of iron, like the side of a ship. The second is to oil or grease it, which is necessary if the object has moving parts like a bike chain. And the third type of barrier protection is electroplating, which is kind of complicated, but basically involves using electrolysis to cover the iron in a thin layer of another metal, which will protect the iron underneath. The other option is called the sacrificial method. This involves adding a more reactive metal, like aluminium or zinc, to the iron. This means that if the object gets exposed to oxygen, the more reactive metal will be oxidized instead of the iron, and so the iron won't rust. An example that uses both of these methods is galvanizing. This involves coating the iron object in a layer of zinc, which is effectively the barrier method, because it's forming a protective coating around the entire nail. However, if the zinc coating gets scratched, and the underlying iron gets exposed, the zinc will still react with any oxygen that goes near the nail, because the zinc is so much more reactive. So it's actually an example of the sacrificial method as well.
I forgot to say that cathodic protection is called cathodic protection because if the zinc is being oxidized, then the zinc is the anode. What does that make the iron? It makes it the cathode, which is why it's called cathodic protection. The electrons that leave the zinc move into the iron and prevent it from losing electrons. Yes?
Is the process what, like oxidation reactions are
Yeah. I mean, oxidation is really putting oxygen on things. That's one of the ways that things are oxidized. So if you're looking at a reaction where you have Mn2 plus and now all of a sudden it's MnO4 minus, you had no oxygens, now you got a whole bunch of oxygens, Mn has been oxidized.
Why is oxidation so special that it gets one category and make that?
Because it is plentiful and very reactive. Yeah.
Anyway, that's everything for this video. So if you enjoyed it, then please do give us a like and subscribe, and we'll see you again soon.
Okay, so that was just a very quick little thing. Do you want to watch Mr. Colger in the last 10 minutes? Yep, good. Okay, we are watching WCLN Corrosion Prevention. WCLN Corrosion Prevention. There we go. Yes. If something rusts underwater, yes. Oh, yes, there is. It's dissolved in the water. It's how fish breathe. Yeah? So the water does have dissolved oxygen in it.
Which consists mainly of iron, is a major problem in our society, but steps can be taken to prevent it. The causes of corrosion of iron and the factors that increase it were outlined in the previous video. Corrosion, its causes. Knowing these will help us find ways to prevent corrosion. Corrosion of iron, or rusting, is primarily caused by exposure of an iron surface to oxygen and water. We can deal with this by painting the surface or coating it with an anti-rust coating and keeping it dry. Painted steel objects like bridges and vehicles must be repainted periodically to maintain a continuous coating. When cracks in paint occur, moisture can collect and rusting can take place quite rapidly. Another cause of corrosion of iron or steel is exposure to any stronger oxidizing agent than Fe2+. This includes all the species above Fe2+ on the left side of the reduction table. So we must do what we can to eliminate exposure of iron or steel objects to these oxidizing agents. Another potential problem is galvanic corrosion. This is where iron or steel is attached to a metal higher than iron on the reduction table, or a less active metal in the presence of an electrolyte. So we must be careful not to attach iron or steel to a less active metal, such as an alloy containing copper, when an electrolyte is present. For example, we must pay attention to what type of bolts or fasteners we use when building steel structures. Corrosion of iron or rusting is enhanced by the presence of acids. So we can limit rusting by keeping acids away from iron or steel objects. This would include protection of the objects from acid rain. When the surface of an iron or steel object is exposed to an electrolyte like salt water, rusting will be enhanced. It can be slowed down or prevented by avoiding exposure to salt water and other electrolytes. Road salt should be washed off of vehicles when possible. Also, protective coatings can be used on vehicles. Finally, when some factors are causing rusting to occur, having higher temperatures can make it happen faster. So when it is possible to do so, we try to keep exposed iron and steel objects relatively cool. Another method that is widely used to prevent corrosion of iron is called cathodic protection. This first type of cathodic protection we'll look at uses what is called a sacrificial anode. This type of cathodic protection is achieved by attaching a metal that is below iron in the reduction table to the iron or steel we're trying to protect. Some metals we could use for this are chromium, zinc, manganese, aluminum, or magnesium. It would not be practical to use these metals below magnesium on the table. They react rapidly with water to form hydrogen gas. Metals below iron on the right side of the table are stronger reducing agents than iron, which means they're more easily oxidized than iron. Remember, oxidation potentials of these are just these values with their signs switched. So the oxidation potentials of these metals are all positive. Notice that as we move down, their oxidation potentials increase from positive 0.45 volts for iron to positive 2.37 volts for magnesium. Notice that these metals below iron all have higher oxidation potentials than iron, which means they all oxidize more readily than iron. So if any of these are present with iron and an oxidizing agent like oxygen appears, these will oxidize instead of the iron, thus saving the iron from oxidation. Let's look at an example. Recall from the video on the causes of corrosion that when an iron surface is exposed to water and oxygen, an iron atom oxidizes to form an iron 2+ cation, which dissolves in the water, and the electrons produced travel through the metal. The equation for this oxidation is Fe solid gives Fe2+ plus 2 electrons. This is the anode region. Oxygen from the air then comes in contact with the edge of the water droplet on the iron metal surface, and it combines with water and the electrons formed by the oxidizing iron to produce hydroxide ions. Because reduction of oxygen takes place here, this is called the cathode region. So the anode region and the cathode region are both on the iron. The anode is the place where iron is being oxidized to Fe2+ and giving off electrons, and the cathode is the area where oxygen is reduced, using up those electrons. We see that rust is formed at the cathode region, and the iron is eaten up at the anode region. The anode and the cathode are in different places, but they're both on the iron. Remember, we had shown that metals below iron on the right side of the reduction table will oxidize more readily than iron does. We'll choose magnesium with an oxidation potential of positive 2.37 volts. We'll attach a piece of magnesium to the iron metal. Because it's lower on the right side of the table and therefore has a higher oxidation potential, magnesium will oxidize more readily than iron. A magnesium atom will lose 2 electrons as it oxidizes to an Mg2+ ion. These electrons flow onto the iron. The magnesium ion will leave the metal and dissolve in the water. This oxidation half reaction taking place on the magnesium is Mg solid gives Mg2+ plus 2 electrons. Because oxidation of magnesium occurs instead of iron, magnesium is now the anode instead of the iron. Oxygen from the air will move to the spot where the iron metal, the water, and air all meet. Oxygen in the presence of water will gain the electrons lost by the magnesium and undergo reduction to form hydroxide ions. The hydroxide ions formed will dissolve in the water. Because reduction occurs here on the iron, this is the location of the cathode. Because iron did not oxidize, there are no Fe2+ ions in solution, so no rust can form. As magnesium is oxidized, the electrons it loses travel through the iron toward the cathode, where they are used up as oxygen is reduced. Looking at the magnesium block, we see that as it is oxidized, it is gradually eaten up. When the magnesium block has been consumed, it is simply replaced by a new one. Because magnesium is consumed in order to save the iron from rusting, it is sometimes called a sacrificial anode. When magnesium is present, it is the anode, so the iron is not the anode. Instead, the surface of the iron acts as the cathode, where oxygen is reduced. That's why the process is called cathodic protection. Here's a photograph of the propeller of a large.
Thank you to students and staff for your flexibility yesterday afternoon and this morning in terms of dealing with the frozen pipes. As mentioned in email, we are clear and facilities are open to use. A couple of updates. The school cafeteria, unfortunately, is not open today. They were cooperating with Waffle this morning. So students and staff will have to make do with some of the community facilities if you are stuck.
If you're interested, he goes on to talk about galvanic protection, and you can watch that on your own at home, okay? The video is listed on page 141.
Thanks again for your
Homework, study.
I'll even feel more flexible.
Homework study.
Homework, study, just study,
Favorite phrase.
right? Just study.
Yeah, I know that. Aaron, why did you help me out? Because I didn't think those were for real. I know work because it was today, bro.
Okay? I love that.
Chat, are you serious? Chat,
Oh,
are
the
you?
video is tomorrow. That's right after school. Always have to talk to flyers.
Oh, that's cool. Why did you help me with the flyer?
Ship. The white blocks are zinc anodes attached to the ship.
I mean, I don't understand that.